I got a blue note saying that. Right. Um, I sat through my office hours yesterday, and I had just one lovely couple come by and visit me for all of 10 minutes. So that wasn't exactly a riveting experience for 3 hours there, but I suppose people haven't really gotten around to doing much yet. One thing, do remember that a string in Espresso is capitalized, so it's the capital S in string for the data type. It will save you. Good evening. Well, it's still mid-afternoon here. See, I get laughed at about the evening thing because when I'm at my parents' house, we eat at 5:30. No, 4:30 to 5. And so that's got to be evening. Everybody's like, that's mid-afternoon, right? So if you're from the southern part of Europe, you wouldn't dream of eating anything until like 9.
See, for me, like evening starts at 5.
Yeah, I think
Anything
evening.
after, like from 5 to 9 is evening. 9 to whenever is night.
Well, I mean, you are a little old-fashioned there, so I think I might push it a little bit. But anyways, so oops, what's going on here? There we go. So string is with a capital S. Just remember that, otherwise things can go horribly wrong. Now, for the rest of chapter 3, I don't want to talk about it. Monday office hours on Labor Day are still on, correct? I'm sure we'll have some questions by then. Who came up with the stupid idea of making it due on Tuesday? I think you did.
You did.
I think Ben did.
We're both pointing fingers.
Right. So since I don't have a life and have nothing else to do, and it's too hot to do anything,
Why not?
yeah, fine. Let's put it this way: if nobody's shown up by 4 o'clock, I quit. So who can we do something evil to if nobody shows up, right? Because somebody's gonna have to pay for my time. That's right. That's it. Yeah, we'll try something like that again. The rest of chapter 3. There's a little bit in chapter 3.11 about how to use the scanner generator tool Flex, which is the one that you're going to be using for the project. Then there's some examples in 3.12 for that little example language in the book. You can look at that as well. Given a implementation of a token and the Flex file as well. And in 3.13, we just go through and write a scanner completely from scratch by hand without doing Thompson's construction and NFAs and what have we not. And you can take a look at that if you care as well. And then there's in 3.14 a handwritten scanner for the little example language. And I think you should look at that. So, are there any questions for chapter 3? I guess we should start with about the scanning that we talked about last time and the time before. Or are there any questions pertaining to the project? And now might be a good time to take those. Hearing none, we'll move on then. Or we can come back later. So now we get to chapter 4, where we will spend an exuberant amount of time. Canvas groups are ready for single submission, question mark? Not yet. Almost. So soon. Every time I say that word, that reminds me of that movie where they had that line that was "Soon, Amy, soon." It was some like horror movie, or I watched as a kid, and I don't know why I still remember it like a million years after. Yeah. Anyways, I never said I wasn't weird. Right. So let's look at parsing, at least to try to sort of get a hold on what we're doing here, and let's just start with a little picture again. Last time my little box was a scanner. Actually, let's draw the scanner in just so we can see if it all fits together. So this is just easier to do when you read it from the other end. That didn't look very nice. So let's try that again. So we have something like that, which we will call my scanner. And we have was it last time? Let me just look up exactly what it looked like. It doesn't matter. I think it was I equals 0, ... And then what had come out of here was something that looked like this, where this was a stream of tokens, and this was just a character stream. Now, for the next part, this stream goes into our parser. And for now, what comes out here is one of two things. It's either that was not going to give me enough space, so let's say not syntactically okay, or we get a green tick mark. We could also get parse trees, and we'll look at that for the next part of the project. So we'll talk about that on, well, actually, I'll make the video available on Tuesday. Or if the video is available, you can just go through last year's video stream. But that's what we're gonna do. And we'll talk about two kinds of parsing. We'll talk about something called LLK and LRK. And let's just go through and look at what these letters are. You might have heard about this in 456, probably. Does anybody remember what these letters mean? No. All right. LR is bottom up. Yeah, so that's true. Let's put those names down. That's a good point. So this is, oops. That's bottom up parsing, and this is top down. Now, does anybody know, so let's see, leftmost left to right. Is that for LL or for LR? Oh, that's a stupid question. That is, of course, for LL, right? Yes, you're right. So this first L here, okay, we do this in red, that one there is left to right scanning. And really, all that means is that you read the input from top to bottom or from left to right. That makes sense because that's how the file is organized. And what color should we go with? Orange. That LL there is a leftmost derivation. And that K is K look-aheads on the token stream. Right, so now we can probably draw the conclusion that that L, that first L there is left to right scanning. What do we think the R is then? This is one of the few places where I get to trick people into saying something that isn't quite right. I shouldn't say that before they radical. Yeah, it's left to right radical scanning. That's exactly what it is. left to right scanning. No, we already did the scanning part. That was left to right, right to left, right. So Marian says rightmost, right? So it could certainly be a rightmost derivation. So let's see, we're in the right color. Rightmost. Now the problem with doing a rightmost derivation, if you just, we'll come back and talk about this much more, but if you just think about it, if I give you a sentential form somewhere in a derivation of a string, and remember a sentential form is a mixture of terminals and non-terminals, and I say, hey, match that to some input, and I tell you that the next step you have to take in this derivation has to be a rightmost derivation step. So you have to replace the rightmost non-terminal by something. Well, that means that you're going to have to sort of look way ahead into the input in order to find it, and that just doesn't seem to work very well. What we want to do at any given time is really match up what's closest to the input. So this is the rightmost derivation instead of a regular one. It's in reverse. And if you think about doing a rightmost derivation in reverse, what does it mean when you do bottom up? Well, that means you are, if you think about the parse tree, you're saying, oh, I've got some leaves here. They make up a right-hand side of a rule. I can now go backwards in the derivation. So I'm building the parse tree from the bottom and up. And my derivation becomes reversed because I say, oh, I've found all the right side, all the bits that make up a right-hand side. And now I found the left-hand side that exists in a rule that has exactly that on the right, and then we can conclude that those things make up the left-hand side, so we're going backwards in that way. But we will come back in full force, and this is K. K look aheads on the token stream as well. Right. So let's start with the top-down parsing LLK. So 4.2 top-down LLK parsing. Now, let's say that we didn't know anything about this at all. So let's start with an example here. Well, I suppose we don't know anything about it. Well, not very much. Let's consider this regular expression here. So A star, B star. And if I ask what's the language generated by A star, B star? So what is the set of strings that can be generated from this? Well, we can do no A's and no B's. That's an epsilon. We can do an A and no B's. That's an A. We can do no A's and a B. That's a B. Then we can do two A's and no B's. We can do an A and a B, or two B's, etc. Okay? So, just to remind you that it's certainly okay to have regular expressions and context-free grammars that generate a set of strings that is infinite. However, the grammar itself has to be finite. We really need to get that change made in the dictionary. Is it not on the board? Finite versus infinite?
Infinite.
It is up there. Words to fix, right?
Yeah.
Yeah.
Huh?
And the spelling of compatibility?
Uh-huh.
Yeah, that's stupid too. I don't know. So yeah, we're working on that. You'll be told once we succeed. Now, can you write a context-free grammar that generates the same language? Oh, actually, you know what? Let's just do something here just for fun. I'm going to ask the following question: is any regular expression also a CFG? I mean, that's not how we should word it. We should say is any language that is generated by a regular expression also generatable by a context-free grammar. And before I even finished it, I've seen a bunch of yeses. Why? You have to be careful when you just say yes willy-nilly. Well, you can't just say because a context-free grammar encompassing regular expressions. That's what I'm asking you to prove. You can't say A, is it true that A implies B? Yes, because A implies B. You can always create an NFA from a regular expression. Can we? You can always create an NFA from an RE. Yes, that's right. Yes, of course you can, because they're dual, right? But that doesn't prove that every regular expression can be written as a context-free grammar. If you remember the Thompson's construction algorithm, what did we do there? Well, we said, okay, if I have this regular expression, what does the corresponding NFA look like? So I gave a constructive proof that I could create an NFA for every regular expression. Can I give a constructive proof that I can create a context-free grammar for every regular expression? I think we might be able to. We could at least give it a go. So let's see, we have regular expression here, and we have a context-free grammar here. What's the simplest regular expression we could think of? How about just epsilon? Can I create a context-free grammar that generates just epsilon? Yes, Michael, you're right. Now, is a PDA just an NFA with the stack? It might be. So anything at PDA could generate anything that an NFA can. Probably. I'd like to show you why. So can we do that? Yes, we can. Here it is. That's easy. Over here, we'll take the next simplest thing, which is just a terminal, and just keep that thing in mind that Michael just said about that a PDA, which recognizes context-free grammars, is, and I'm going to take the liberty here of not using NFA, but say DFA, because I think PDA is deterministic. Yes. DPDAs. So we're going to say DFAs plus a stack, and we'll see how that can be important in just a second. Right. So there we go. That's the base case. Now, what else can I do in a regular expression? I can say S concatenated with. Oh, I'm going to use something else. I'm going to say U concatenated with V. I'm going to say U or V. Actually, let's do this one first. So if U goes to something and V goes to something, then S can go to U, V. All right. U or V. Using the same U's and V's up there, we can do that. And then we just have U star. Well, that's just S goes to. And now, now we have a choice. Shall I say U, S, or epsilon? Or S goes to S, U, or epsilon? In reality, it doesn't make any difference. what I do want to draw your attention to is this is the only rule. This is the only rule that has recursion in. You see, that has no recursion, no recursion, no recursion, no recursion. And if you think about it, these UVs cannot have recursion here or here, because that U is a new non-terminal to take care of that, and that V is a new non-terminal to take care of that. So when I generate these context-free grammars from a regular expression, these UVs are going to be above S where they're used, and the only place you can get any kind of recursion is here or here. So you can never have any indirect recursion. So you can't have something where you say S depends on U, which depends on S, which depends on U. That's not possible, because this is the only place we have recursion, and here these are always defined before they use them, before they're used. So I get the best I can do recursion-wise is that. So what if I say the following here? No regular expression can generate a grammar that looks like this. So I'm just going to put U, S, V. U is there, V is there. So that is a situation where there is something on both sides of S. Does this ring a bell to anybody about anything? I'm sort of trying to jumpstart your memory without giving you all the information. I think there should be some light bulbs in it. That doesn't sound more like an old engine, I guess. If I could generate, well, so if we look at it, it's pretty clear that that's true. Whenever I use these rules to translate a regular expression into a context-free grammar, I can never get in a situation where I have this, because I can only ever have that sort of thing when it comes to recursion, right? So what can I do if I could do this? Well, oops, I can do something like S goes to A, S, A, or epsilon. Okay, well, I could also do that. What's the language of S? Isn't that just AN, BN, N greater than or equal to 0? Which is not a regular expression. I bet you were shown that this was not a regular expression using the pumping lemma or something, which nobody seems to be able to remember, right? So this might not be entirely as pedantic, but I think it shows us that we have definitely a pattern that we can generate using these rules, which means that there are languages that are context-free but not regular. We've been postulated that this is indeed one of those languages, and that grammar here is the smallest grammar that can generate that, and that shows this pattern that we can't possibly do using any of these rules. So there's no regular expression that uses these three constructs in these two base cases that would allow me to create this. Therefore, that language is not regular. Right, so can I now turn this into a regular expression? Yeah, sorry, a context-free grammar. S goes to A. We like to have a special start symbol. A goes to, well, I got to do A's, little a's, and then when I'm tired of doing that, I got to do the little b's. So A, or capital B, B, or epsilon. Now, of course, I could have said A, and B, but that doesn't matter. That's fine. Okay. Now, would you be okay with the following statement? For a context-free grammar G and string W in sigma star, we can say that the string is in the language generated by the grammar if and only if, I just put something in here, with start symbol S, if and only if S in a number of steps, a very nice S. If S in a number of steps, then become W. So this part says that I start with S here, and then I take a step, and I keep taking steps, and then I end up at W. And when I do this, I never make a mistake. If W is in L of G. So in other words, if the string is derivable, then no backsies. You can't say, oh, that wasn't right, let me go back and try something else. I mean, I suppose we could come up with a whole bunch of strange ways of determining whether this is the case, right? I mean, if I look at W and I say, right, in order to determine whether this is the case, i.e. whether this is possible, then I can figure out whether this guy here exists by looking at the length of W. So let's say that is n. Then I can just look at all derivations of length n or less and go and check to see if any of those derive W. How would that work? I mean, would that be a viable way of doing it? And how long would that take, time-wise? A long time, right? Because every time I have a non-terminal in my sentential forms here, then I have to multiply by the number of different options there exists for right-hand sides. And typically there's at least two. So this becomes something that is in the order of 2 to the power of n, which is probably not a viable way of doing this. So we gotta come up with a situation where we can do this without making mistakes if the string is in the language. I mean, if the string is not in the language, then it's all a big mistake, and then we won't be able to get to W, and that's fine. But if W is derivable, then we gotta go in a straight line straight to it. So let's sort of try to come up with some things that have to be true about the grammar for this to ever work. So So let's say that I have something like, oops, A goes to little a, or, oops, B, B, and B goes to something. Right, and then I'm going to ask, is little a in the language of A? No, 1 out of 71? Oh, one person is still, yes it is. Right, so we'll give that a green tick. Actually, we can say A goes to A. All right. Is B A in the language of A? Is A B in the language of A? This one we don't know. Because I didn't give you any information on that. Yeah, so that totally depends on what B goes to. Is AB in the language? AB for sure not. What, how for sure not? That's you sound very confident on that one. Assuming A is the start symbol from, yes, so let me just say a quick word about that. If there's no S goes to something on the first line, then we always, by default, assume that the start symbol is the top left non-terminal. So yes, we will assume that A is the start symbol here. So if A is the start symbol, then why can't I have AB in the language of A? So Louis says, because the only production rule of A that can generate A's, and A does not have a non-terminal continue looking for input. Yeah, so no, but we have to try. This grammar is small enough that you can actually make that determination by just looking at it, right? So let's see. Daniel says A is a terminal with no non-terminal connected. Well, following. So if A generates little a, that must be the end of the sequence. Correct. Could B go back to A, then could generate an additional A? Yes, B could certainly go back to A, but I need something here that starts with an A. And if we look at this, if I start a derivation down here, then what is the next step if I'm trying to derive a B? Well, the next step is that, right? So what happened there? Well, I got that guy matching this one, and then we can't go any further because we haven't got any more non-terminals. So yes, that observation is indeed correct. So this is not a correct derivation, but luckily the string was not in the language, so it was all right. Now, why couldn't I just go try this one? Well, because that starts with a B. So just looking at this, we can probably say something along the lines of, if the first thing of the string that I'm trying to parse matches the first thing on one of the right-hand sides here, then I know which one to pick. For example, for this A, I know that I shouldn't pick this one because this always generates something that starts with a B. What about this one? Well, B there. Well, it's certainly not that one because that would be an A. So we would have to go with this one. So now I'd end up saying, well, that B matches this B. That means that this B has to generate that A. So when I get down here, if this starts with an A, then we're good. Otherwise, then we're not good. Now, what about this then? See, this was easier to do on when we used the real boards because then I could write stuff there, and then I could stick a piece of paper on and hide it, and then that proved that I had thought about it before I revealed it. Now I can't do those tricks. I don't know if there's secret paper or write with clear ink, and then you can release it. So what about S goes to a X or a Y?
You could always like share another window and then kind of.
Oh yeah, I can move it over. Yeah, that's right. Oh yeah, that's not a bad idea. Yeah. All right, it's still doable. Right. So if I got this and W, yes, no. Jeffrey had a hand up and then he started sitting on it again. Oh, that was probably just the. Did your head hit the keyboard? You fell asleep. We only have the fun we make ourselves. That joke works better in Danish. Right, and W is equal to a B, for example. Now I can ask, is W in the language of S? And we get the same sort of thing that we had before that said, well, it depends. If X can generate something that is a B, then yes. Or if Y can generate something that's a B, then yes. All right, so maybe I should tell you what, let's see. X gives us a C, and Y gives us a, let's make it a B. We can make this, let's make this a little bit more interesting. Let's make it like that. Okay, so is W in the language of S? Yes, yes it is. Right, so now actually, let's try something, yes, but now look at the following. And now I'm going to have to do what Ben suggested, because otherwise this thing won't work. So I'm going to go in here and I'm going to, actually, you know what, I should have learned by now to make this as big as possible, right? Because that just makes sense. And I'm going to go in and share. Yeah, that didn't work. Where's my sharing window? Oh, I screwed it up now. That doesn't work. Oh, damn technology. There we go. Terminal. Yeah. So now you can't see what's under here, right? But you can hear me twice. So let's see. Now I just got to figure out where it's safe to write. There. So if I say W is equal to this, and I show you that much. And now remember, if this string is in the language, then we'd like to be able to determine that without backtracking, right? Because if we have to do the backtracking thing, then we might as well try all the options, and it just becomes very expensive. We'd like to be able to do this in sort of a linear manner. So S goes to, what's the next step? AY. How do you know that? Thought you'd found a way to look under my terminal.
Yes.
Well, how do you know that this has B's in, right? I wrote a new one. Right, so this is not the AB that's above. This is a new one that also just happens to start with an A. Yeah, it's not the same one. That would be too easy. That's like asking, that's like asking people in quiz shows questions that they've just been given the answers to. We don't do that. There may not be a B. There could be some C's or some Q's or who knows, right? So if I have to make the right step or the right determination with this information, and this is exactly what the look ahead is, because what is my look ahead here? Well, it's just one. I'm only allowing you to look ahead one, which is what is the next thing on the input. So with just one look ahead, can you tell me what the next step is? No, you can't, because the next step, actually the first step here, is either AX or AY. But if it's AX, then I have to have C's or nothing. Or if I go S goes to AY, then I have to have B's or nothing. And that's in itself a little bit of an iffy affair if I have the ability to generate the same string. So epsilon, for example, here, sorry, A, just a single letter A can be generated by S goes to AX goes to epsilon, or S goes to AY goes to epsilon. So I end up with A being doable in two different ways. So what would you like to know more in order to make sure that you do this right? So we can definitely say here, one look ahead is not enough. Why is it not enough? Hold on a quick second, Ryan. I'll come back to that question in just a sec. So why is one look ahead not enough? Well, one look ahead is not enough because that starts with an A and that starts with an A. So if I see something that starts with an A, then looking ahead one is not enough. Is it enough to look ahead two? Well, the grammar we have here. For this one, yes. You'd think so, because if I well, so why do you think it's okay for two look aheads? So why is it okay for two look aheads? So Daniel says it will be more than two because it could be A, AB, ABB, ABBB. Well, yes, but it isn't all of those at any given time. It's one of them. So that doesn't work because you're not trying to parse a whole bunch of different strings. The string is given, right? So this string exists. You just can't see it. So Louis says, oh, wait, but could it be just an A and it wouldn't tell which to generate next because X and Y can both generate an epsilon? Exactly. That's the only little caveat about this one. But not caring, if we don't care about that, then we can get pretty far by just looking ahead too, right? Because if I tell you what the next one is, and I say the next one is a B, well, I know that if I need that A matches that A. Now, can this X generate something that starts with a B? No. Can that Y generate something that starts with a B? Yes, it can. So there's only one option here, and that is to say, oops, maybe we'll do that in a different color, a Y. Now, with one look ahead, I know here that that y has to become that. Now, what should I do about that y? Well, we've got matching here and here, so we better look at the next one. That's the b. All right, well, that becomes fairly easy because I have to replace the y by something that can generate a b, and I have two options. That's little by or epsilon. And epsilon definitely is not a b, so we'll go a, b, b, y. Now what? Well, I got to tell you what's there. Well, there's nothing else. So that's the epsilon transition we'll need to take, and then we get to that. Now, that is indeed true. So 2 is mostly enough. Though not for w equals a. Just like Louis said, if it's an a, we can't tell which one to which step to take, because s goes to ay and s goes to by are both good. Sorry, s goes to ax or s goes to ay are both good because both x and y can become epsilon. So it's not deterministic which one to take there. So it's ambiguous. It's not non-ambiguous. It's ambiguous. Now, if I can do this trick and always determine what is the next step by only looking one ahead, then I have an LL1 grammar. If I can do it with 2, that's just an LL2 grammar. This one is not quite LL. Well, it wasn't LL1. It's not quite LL2 because I can't determine it with 2 look-aheads. Can I do it with 3 look-aheads? No. So this grammar is it's ambiguous. Now, can I make it into something that works better for me? So maybe we could say here, can it be made LL1? So can I fiddle it in such a way that now all of a sudden I can do it with just one look ahead? Is that what Chomsky normal form is? No, I don't think Chomsky normal form has anything to do with LL-ness. But I could be wrong. You're catching me out on something that isn't really my field. Chomsky normal form is when you have maximum 2 things on a right-hand side, I think. You know what? Can we just hold on a second? I bet you, if you look it up in the back, A, B, C, Chomsky normal form, page 244. Ha! I was right. Yeah, either S goes to epsilon, A goes to little a, or A goes to BC, where BC are non-terminals. Yeah. See, I do remember stuff. So the answer is no. Now, what is it we can observe from this? Well, we can observe that no matter what you do, you must start with an A. So could we not say S goes to A? And now basically just make a choice between X and Y. And if you don't like writing it like that, then we can say S prime, and then S prime is X or Y. Now, is that LL1? So can I always determine what is the next correct step, no matter what I see on the input? Well, in order to figure that out, I probably need to see, well, we retain these, and now we have these here. Now, why was it that this didn't work? Well, if I had an A, I couldn't tell which one of those to pick. All right, if I have an A, can I tell which one to pick? Yes, you pick this one. If you have anything but an A, then you're in trouble. All right, good. Let's do these up here. If I see an A, can I tell which one to pick? Yes, you pick the epsilon. See a B, epsilon. C, that one. Anything but C, you pick that one. Anything but B, you pick this one. Now, what about this guy? S prime it's not null, it's epsilon. And no, it wouldn't, because I've just lifted this A. Oops. Damn it. I've just lifted this A out in front, right? So basically what I had was S goes to A and then bracketed X or Y. Now, are there any doubt about which way to go here? So if I see an A, which way should I go? Well, then we're in trouble because neither of these can generate A, so that's fine. If I see a C, well, this guy can't do any C's, that one can, so we'll pick that one. If I see B's, then we go that way. What if I see an epsilon? What if I see the end of file and we're done, we have no more? Well, this can produce an epsilon, this can produce an epsilon. So still not good. Can this language be made LL1? Well, what is this language? So let me just, oops. We'll just copy it in here so we know what we're talking about. Okay, what does this language look like? If maybe we can better figure this out if we can get a grip on that. What does the language of S look like? Well, it's A followed by C star or B star. Now, one thing we have to keep in mind, so Daniel says there's nothing you can do to know which way to choose X or Y when you have nothing, i.e. the epsilon. That is true. Oh, let me just go back to Ryan's question. It says, if you already determined everything that we need with this one, so can we dispose of it and look at the next one ahead? Well, basically that is what we're doing. So once we're doing these steps along the derivation, we say, all right, we're aiming for this. I've decided that I'm going to do this. Then this A is gone and this A is gone, and then now the rest of this has to generate the rest of that. So now I figured that so that A was gone with that one, that B is gone with this one. So now that B has to be generated by that Y alone. Now I got that, I've got that, I'm done. So that means this Y has to generate epsilon, and it did. So yes, that is exactly what you do. So you're matching up things from a leftmost perspective. That's why we're doing leftmost derivations. So yeah, correct observation. Now, if I used the construction algorithm from the previous page, then I would actually end up with this. So that just tells me how to take a regular expression and turn it into a context-free grammar. It does not guarantee that it's LL1. So that's pretty mechanical. To make it LL1, you need to be a little bit more artistic, I guess. So can anyone make this language work so that I can do it without any problem? So the problem, of course, is that epsilon on that both X and Y can generate. And who asked a question ago? Benjamin said, don't we need a, and I'm going to translate that null to an epsilon in S prime. You don't need it, but you could lift it up there, couldn't you? So what if I did this? S goes to A, S prime. S prime goes to, well, let's say that if you have an epsilon, then we'll take it here, and then we'll remove the opportunity for X and Y to generate epsilon. So we can do that. X or Y or epsilon. So I've lifted the epsilon up there. And then we're going to say X goes to C X. But now that epsilon is gone, so I need to put a C there. And now that Y has B, Y, or B. There we go. Have we got an LL1 grammar now? Daniel says yes. What do you think, Ben? Oh, you just had that. You just had that sort of. You just had that strange look on your face, as in you saw something wrong.
Yeah.
So Benjamin says still LL2, isn't it? And Daniel says, doesn't X go to CX or C? Yes, that's X. Now we've just moved the problem. This is a big mess, and now that's a big mess. What do we do then? So Daniel tells Daniel that he's right. It's not the same Daniel though. So he's not talking to himself. Is it doable? Can we do it? Can he fix it? Can you make X S prime and Y? Yes, but probably not S prime on the right hand side. You probably want to be X there. So let's see. S goes to A. S to get the first A. Now S prime goes to, well, either we want to do something that involves C's and then we got to do X. Or we want to do something that involves B's and we'll do Y. Or we'll take the epsilon there. So if I see a C, then I'm forcing to go down onto X here. And here I can do as many as I want, but I can also take an epsilon. And if I do this, then I can do a B here and an epsilon. I think that does the trick, doesn't it? Now, what's interesting here is if we go all the way back to this page here, I said, oh, well, it doesn't matter if you're doing left recursion. Oh, that's not left, that's right recursion. Or you're doing immediate left recursion. Is that true for this grammar? So can I swap around those there, even though this rule is to generate X's and this to generate C's, and this rule is here to generate B's? Would it be possible just to say, so now I have something here which is direct left recursion, which is not always good. It becomes a big problem if we're doing with recursive descent parsers, which we will do next week. So this is probably a better way of doing it. But so is this grammar now LL1? So let's see. We got to check that we can handle. So let me just write down what the alphabet is. It's A, B, C, and I'm just going to put $1 in there as well. And this is end of file. Right. So those are basically the ones that I got to be able to handle for all the rules. Let's see. This rule is fine because there's only one right-hand side, and we can only move on if there's an A. Now, what about this one? That has to start with a C. That starts with a B. That doesn't clash. That starts with a C. That's an epsilon. That doesn't crash or clash. That starts with a B. That starts with an epsilon. That doesn't clash. That's fine. C and epsilon. That doesn't clash. B and epsilon. That doesn't clash. We're good, I think. So it looks like if I only have one right-hand side of a non-terminal, then it's no problem because you're forced to take that route. So if there are any terminals at the beginning, they have to match. Otherwise, we're bad. If I have two choices, then they have to generate things that start with different things because, like we saw up here, it's a problem if I have two right-hand sides of the same left-hand side. Oops, hold on, I just did something bad here. We saw that it's a problem if I have a left-hand side that has two different right-hand sides that can generate strings that start with the same thing. Because if I'm trying to do a Y and the next thing I see in the input is a B, I don't know where it came from. That's how we went through and did this, right? So if I have one right-hand side, no problem. If I have two right-hand sides, these guys can't generate strings that start with the same thing. So to be LL1, these two right-hand sides cannot generate strings starting same terminal. Now, what happens if I have more than two? Well, then it's those two can't have anything in common, those two can't have anything in common, and those two can't have anything in common. So for this one, pairwise, like the last rule. Now, this is a mistake people often make. They say, this, and this can't have anything in common. And if they don't, everything is fine. That's not true. It's got to be these two, and those two. So we got to look at all possible pairs. Now, what about that epsilon and that epsilon? This is we used to call it, before people were so easily offended, we used to call it the trash cannibal offense. That's what when we would throw people in the trash can behind the building. Okay. Yeah. That was just the other Ben. So what about this epsilon and this epsilon? They seem to be generating the same thing. Well, they're on right-hand sides of different left-hand sides, so it doesn't matter. So basically, the rule seems to be something along the lines, and we'll formalize that. The rule for LL1 ness for each left-hand side, no pair of right-hand sides of that left-hand side can generate strings starting with the same terminal. Yeah? Everybody okay with that? Except for the 7 people that we lost. Sort of like sailing a boat once in a while. it rocks a little bit and somebody falls over. All right, let's try another one. So this is example 4.1, and it says S goes to A, B, B, or epsilon, and B goes to B, CB, D. And before we do that, let's define over here. So we're going to define for a sentential form X. I'm going to define a set called first of X, which is basically what we were talking about over on this page. That just says, what is the set of terminals? Oh, Jacob is out of power. Well, just be happy you're not with Cox, and you'd probably be out of internet as well. Which I guess you will be if you're out of power, because it's not a solar powered modem. It should be. Anyway, so first of X is going to be the set of terminals that any string generated from X can start with. So set of terminals in sigma that any string derived from X start with. Never use a preposition to end a sentence with. So we can write it as little a, where X in a number of steps become a W, where A is in sigma. So when we did that, that's basically what we did here when we looked at this and said, oh well, you know, what can S start with? Well, something that starts with A. And then what can X generate? Well, either nothing or something that starts with C. Then we ran into trouble when we had two right-hand sides of the same left-hand side that had anything in common when I looked at their first sets, because this has B in its first set, and so does that. So can we calculate these sets here? So what's first of A? Then what's first of B? Well, we will formalize this shortly. It looks like we're going to do that next time. But there are some things that we got to figure out. That is, if I'm computing the first of A, what is the first of A if I have a number of different right-hand sides? So let's see. If I have A is alpha 1, alpha 2, dot, 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 alpha n, then what is the first of A in terms of first sets of the right-hand side? Well, it's just a big union of first of alpha I 1 to n. Okay. Right. So if A is in sigma, what's first of A? Well, we already used that a million times. That's just A. Okay. Epsilon. What's first of epsilon? Oh, that's just epsilon. What if I have x1, x2, dot, 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 xn? Were there sentential forms? What's first of x1 up to xn? That's the hard one. We'll look at that one next time. But let's give this a go and see if we can sort of muddle through it, and then we'll sort it all out next time. Right. So first of A. Well, let's see. First of that one must be just A. First of that one is just epsilon. First of that one is just B. And surely first of C, B, D is what? Yeah, it's just a C. Why? Well, because C is a terminal, right? So everything generated from little c, capital B, little d, starts with a little c. Okay, so now we have what we need, at least for the bottom one. We got a B there and a C there, and we have that rule that says in order to calculate the first set of that, you take this first set and you union it with that first set. All right, so that's easy enough. So this is just first of B union first of C, B, D, which is B union C, which is BC. Right. Now, there's just one left, which is this guy here. What's the first of B? So any string generated from, from capital B, little b, is going to start with what? B or C. Yeah, B or C, because it starts with whatever strings from capital B start with, and we already calculated they start with B and C, so we get that. So this is the first of A union first of B, B union first of epsilon, which is A union B, C union epsilon, which is A, B, C, epsilon. Is this grammar LL1? Well, we can fairly easily check. Does this first hand side have anything to do with that first set? Nope. No intersection between those two. What about between those two, A epsilon? Nope. What about these, B, C, and epsilon? Nope. What about B and this one here? Well, that's just a B and that's a C, so no, we're good. Okay, now I'm going to do this one more time because I just have 2 minutes. So I'm going to say following. But what about A goes to A, B, B, oops, B epsilon, B goes to B, C, B, D, or epsilon. So I just added this epsilon here. I'll do that in red. There we go. Okay, off we go. First of B is B. First of C, B, D is C. First of epsilon is epsilon. LL1 check. They don't have anything in common. They have nothing in common, and they have nothing in common. So B's fine. All right. First of A is just A. First of epsilon is just epsilon. First of B. You know what? I'm going to make another change. I'm going to change that to a letter we haven't used, a little e. What's first of B, E? Now, if I go back to this page here and I change this to an E, I get an E there, I get an E there, and nothing else changes. It stays exactly the same, right? So what is the first set of this guy? So what can any string generated from this start with? Daniel says the middle and top becomes BC epsilon, which is a problem. Well, if it does become BC epsilon, then it is a problem for LL1ness. But remember, epsilon is only ever in a first set if the sentential form can generate epsilon, so if it can disappear. Can capital B little e ever derive epsilon? But first of BE, I am going to say here, right on the end of finishing, cannot contain epsilon because B, capital B, little e cannot generate epsilon. So I can certainly say that BE cannot generate epsilon. If B in a number of steps become epsilon, then BE becomes just E, right? So that epsilon doesn't follow through in the first sets unless the entire thing can become epsilon. So here, for this guy, I still get B and C, and then I get E, which is this E because epsilon is in the first of B. So that complicated rule we had down here is actually the rule that we used on this. So it has to read something along the lines of the first set of this is included, except for epsilon. But if epsilon is in there, then I got to look at the first set of this, because this b having an epsilon in its first set means that it can disappear in a derivation, because that b could take that epsilon, and now be has become e. So now strings generated from be can start with e. So first set of that minus epsilon is in the first set of be. But if epsilon is in b's first set, then we grab the first set of the next thing without an epsilon. But if there's an epsilon in there, then we look at the next thing, and so on and so forth. And only if all of them have epsilons in their first set do we put an epsilon in the final thing here. And I think that is exactly where we should stop now, and then we shall formalize this into some reasonable formulas to work with next time. But we have everything we need in order to actually write that down. Any last minute questions? Oh, now Ben is taking out the isopropyl alcohol. This is gonna this is gonna turn serious. Yeah. Good thing the lecture is over, so we can have a. I think I might have some acetone as well. No, I only got the pads to do the nail polish removal thing. I'm telling you, if you were here, that would be the place to be. All right, guys. I will see. What is it today? Thursday. So I guess I'll see the few unlucky ones that want to come to office hours on Monday, and the rest of you on Tuesday. So have a good weekend and enjoy Monday off. Oh, wait a minute. You're not supposed to enjoy Monday off. You're supposed to be working.